It's my pleasure to introduce you to Vertex Transplants on a Convex Polyhedron. It's a somewhat unusual paper, I think, in that it doesn't address a problem in the literature, and it doesn't really lead anywhere particular. But I hope you can find some enjoyment in it nevertheless. Starting by illustrating the main idea on a regular tetrahedron. Here's the regular tetrahedron unfolded. Here it is in 3D. You connect a point X to a point Y by a geodesic, two geodesics of equal length, and that forms what's called a digon. The digon surrounds this vertex V0, and you remove that digon, resulting in this, and you refold the digon surface into a doubly covered triangle and glue it into here. And the result is a new convex polyhedron, which is a 6-vertex irregular octahedron that results from the gluing. Avogadro's gluing theorem, which says that if we glue polygons together along their boundaries to form a closed surface homeomorphic to a sphere, and such that no point has more than 2 pi incident surface angle, then the result is a convex polyhedron uniquely determined up to rigid motions. But there is no constructive procedure for calculating the 3-dimensional shape guaranteed by this theorem. So only in small or symmetric cases can we actually construct the shape. Result of the paper: one main theorem: for any convex polyhedron of sufficiently many vertices and no vertex with curvature greater than pi, there is some vertex v sub 0 that can be cut out along a digon of geodesics, and the x-sized surface glued to a geodesic connecting two vertices v1, v2, and the result is a new convex polyhedron with 2 more vertices, and 16 vertices suffices for this theorem. And now we'll go through some more examples. So here's cutting out a digon to include one corner of a cube, and the length of the digon, this is a unit cube, is 1, and this folds to a doubly covered triangle, which can then be sutured into any edge here, v1, v2 of the cube. The result is once you apply Alexandrov's theorem, is a 10-vertex, 16 triangular facet polyhedron. Alexandrov's theorem works for doubly covered polygons, and here's a doubly covered square where I've just cut out a diagonal of length 1 and then suture it back in over here, and you get another flat polygon, this time a hexagon, so a square goes to a hexagon, 2 more vertices. Perhaps more interesting is this example where this is the front, this is the back. Fold the back over, and you'll see that x and y are right in the center of the front and the back. So here's one geodesic up gamma 1 and then down to y, and the other this way. So that's the digon removing v0 and then suturing in the doubly covered triangle to here. Now this is one case where it's so simple that I could construct the 3-dimensional object polyhedron implied by Alexandrov's theorem, and here it is. If x is all the points that have 2 or more shortest paths, shortest geodesics to them from x. Imagine x, here's the shortest path, shortest geodesic to v0. If you aim slightly left of v0 and slightly right of v0, you form a digon, xy. If you unfold that digon around v0, you get a picture like this, and it's easy to use Gauss-Bonnet to conclude that alpha plus beta is the angle deficit, the curvature at v0. So what we will do is move x along the geodesic to V0 and slide y along S in the previous figure so that at all times the distance is the same. Permit a vertex transplant because the lengths match between the distance between V1 and V2 and the digon length. And when you suture in the digon into V1, V2, the curvatures remain positive. And that's because we chose omega 0 to be smaller, the curvature at 0 to be smaller than at 1 or 2. Three conditions we need to achieve in order to guarantee that there is a vertex transplant. First, the curvature at V0, the vertex being transplanted, must be smaller than that at where it's going to be inserted. The digon lengths have to match the distance between V1 and V2, and finally, V1, V2 should not cross the diagonal. So we achieved one by actually choosing V0 to be the vertex with the minimum curvature over all vertices. So automatically we've achieved that. For step 2, for the lengths, the main idea, the danger is that the length could be too long. So we choose V1 and V2 to achieve the smallest nearest neighbor distance over all pairs of vertices excluding V0. And then we prove that the nearest neighbor distance that we're using here is at most half of the diameter. And then we prove that there is a point such that the distance between x and V0 is at least half the diameter. And then finally, for the crossing, we show that if it crosses, there's another point that can be found that avoids the crossing. Prove any of those claims, but I want to show you the lemma about the furthest distance. So the diameter of a polyhedron is the length of the longest, shortest path between any two points. And for any point on the polyhedron, the distance to a furthest point is at least half the diameter. So this is easy to prove, and we use this in the preceding argument. Skipping all the way to the crossing, this is just an image that shows you crossing avoidance, one of the technical aspects of the proof. But I'd rather move right on to the open problems. So recall, here's the theorem that there always is a vertex that can be cut out along a digon and glued into elsewhere to result in a new polyhedron with n+2 vertices. And there are a few conditions. You have to have sufficiently many vertices, and no vertex can have curvature greater than pi. So here are open problems. Extend the theorem to all convex polyhedra. So this is an artificial constraint, and I think it can be reduced to 4, and maybe the curvature restriction can be removed. I have very specific conditions, restrictions, to allow me to find this triple of vertices and make it all work for a successful transplant. But it's not at all necessary that these be satisfied. There's much more freedom that I'm not exploiting because I can't control it. And that additional freedom might permit controlling the shape changes. We saw a doubly covered square get transplanted into a doubly covered hexagon. When does that happen? When does a vertex transplant always produce another doubly covered flat polygon? What limit shapes are realized as you repeatedly vertex transplant? Each time the number of vertices goes up by 2, and each time we get a new smallest curvature vertex. Does the transplant always increase the volume? It seems that the overall effect is to round the surface in that V0 doesn't change, but you introduce new small vertices and you flatten V1 and V2. or move them towards flat. Can the theorem be generalized to transplant several vertices at once using the same diagon? For example, you can have a diagon to include the endpoints of one edge of a cube, a single diagon, and if that's of length √2, you could then suture that into a diagonal of the cube. Thank you.